And we welcome you to yet another lesson in Math 222 at SUNY Geneseo. On today's show, we're going to take a look at how to integrate powers of trig functions. And just trying to keep things in perspective with us here, Chapter 8 of Thomas's calculus book talks about techniques of integration. So most of the lessons through this week and into next will be all about, here's an integral, how do I find it? Uh, Much more valuable in times past than today with all of the tools at our disposal, but still valuable today because who the heck wants to be tied to a machine forever? Said the man sitting in front of a machine talking to you. So what I'd like to do is I'd like to take a look at integrals of the form sine x to some power cosine x to some other power dx. And there are three cases for us to consider, and we handle them differently. Case one is the case where m is odd. So the sine x is raised to an odd power. Regardless of what this is, if m is odd, there's a way to deal with that. Case two is the case where m is even and n is odd. So maybe this is even, but this power is odd. And then case three, m and n are both even. And the tricks are slightly different in each scenario. The techniques we use are slightly different. In case one, we're going to break off a sine x and use the fact that sine squared x is 1 minus cosine squared x. This is that big trig identity from your work in pre-calc. We're going to break off a sine x, sort of leave it hanging out as a free radical, and use that trig identity. In case two, we're going to break off a cosine x and use the same trig identity. And you're going to say, that's not too bad, that's not too bad, which leaves you wondering when the other shoe drops. And the other shoe drops down here. We're going to use double angle formulas down here. 1 minus the cosine of the double angle over 2. Cosine squared x is 1 plus the cosine of the double angle over 2. So really, I'm going to show you how each of them works, and you're going to say, this I can do, this I can do. Gosh, I hope this doesn't get picked for exam day. So here's a case one. You've got the integral of sine cubed x cosine to the fourth x dx. Now the trick, the technique, was to break off a sine x, sort of leave it hanging out here. What advantage is there to leaving a sine x hanging out here? Well, it's not obvious. Well, let's see what the rest of the trick says. The rest of the trick says to sub in, instead of sine squared x, 1 minus cosine squared x. Is it obvious yet why this is hanging out here? Is it obvious yet why sine x is sort of hanging out here? Yeah, now you've sort of figured out that this is the du, sort of, because if u is cosine x, du is the negative of sine x dx, and so this thing is the negative of the integral of u to the fourth minus u to the sixth du, and that, to the best of my knowledge, is negative u to the 5th over 5 plus u to the 7th over 7 plus a constant, and we don't ever leave those integrals in terms of u, and so you've got negative cosine x to the 5th over 5 plus cosine x to the 7th over 7 plus a constant. And this will work every time the power on sine is odd, because you can always break one off. What's left is an even power of sine x. This trick works, and it's a u substitution. So I could do 12 examples, but they'd all be substantively the same. In case 2, remember, case 2 was that m is even and n is odd, so something along these lines: m is even, n is odd. And so you're thinking, well, I can do this. The technique said that I'm supposed to break off a cosine x. And I'm pretty sure you know why that is sitting there. That is sitting there because I need this to be the du where u is sine x. This is not in terms of sine x, but it could be. It could be. And in fact, this looks very similar to the case 1, and that's by design. What do you got? You got that u is sine x, you got that du is cosine x dx. This is in terms of u, this is the du, so you have the integral of u squared minus u to the 4th du, and that is 1/3 u cubed minus 1/5 u to the 5th plus a constant, and I know exactly what that is. We sub the u back in. If the power on sine is even and the power on cosine is odd, breaking that one off makes a u substitution happen. And really, that's the thing I want you to figure from all this. I don't want you to memorize a bunch of things. I want you to think, hey, I know how to leave a du handy for myself. And if one of these powers is odd, I can leave myself a du, and trig will help me see the u. So what happens in case 3? Well, case 3 is when you've got something like this. There's no cosine to break off. There's no sine to break off. It's just this. And the best way I can think of to go at this is to recognize that this is cosine squared x times cosine squared x dx. And each time we can use a double angle formula. Cosine squared x is 1 plus the cosine of the double angle over 2. Going to do a couple of things. Going to pull out the 1/4 because that integral symbol is a semi-permeable membrane. And what have I got in here? 1 plus 2 cosine 2x plus the cosine of 2x squared. That in itself is a double angle substitution. So you've got 1 plus 2 cosine 2x plus 1 plus the cosine of that double angle over 2. And it's at this point that I think to myself, I can integrate that, I can integrate that, I can integrate that, I can do this. The integral of 1, got it. The integral of 2 cosine 2x, got that. Took me a minute, needed to do a u sub in my head. plus, I can do that. A little bit trickier, but I can do that. Plus a constant. It doesn't have to look nice. It just has to be right. So when the power on sine and cosine, when the powers on sine and cosine are both even, this is your only ticket out that I know of. So you're kind of hoping that this is not picked for the exam. Everybody keep your fingers crossed. One other thing we should pay attention to. Sine and cosine are not the only functions in the world. There is also tangent and secant. Let's go purple. When you go tangent and secant, we're looking to use the fact that secant squared x is tangent squared x plus 1. So, for example, if you're looking to integrate tangent squared x, you would recognize that, go back, orange. You would recognize that as the integral of secant squared x minus 1, because that's tan squared x. So secant squared x minus 1. So here's the question. Do I know the antiderivative of that? Oh, you bet I do. And I can do that. And that's not hard at all. We use the trig to get us something whose calculus we can handle. Also, sometimes it's secant squared that we can integrate. Oh, purple. Other times, we think to ourselves, it'd be really nice if there was like a secant x, tan x just sort of hanging out at the end. And that would be great because this is the derivative of secant x. But what would be left over here is a tan squared. Oh, but that's okay because tan squared is just secant squared x minus 1. So secant x is the u, this is the du, this is the integral of u squared minus 1 du. And that's 1/3 u cubed minus u plus a constant. So the same kinds of things apply. We either try to give ourselves something whose derivative we're familiar with, or something where a du makes a u substitution really slick. So, some things for you to consider. The integral from 0 to 2 pi of sine squared x dx. That has to be doable. The integral from 0 to pi over 2 of sine cubed x cosine squared x dx. And the integral from negative pi over 4 to pi over 4 of secant x to the 4th dx. And if it helps you at all, and it probably doesn't, one of the answers is pi, one of the answers is 2/15, and one of the answers is 8/3. And I'll let you figure out which is which. So that's 15 minutes of video watching, plus whatever you did to rewind and go back. But this should take us another 10 or so. Hit them so that when we get to class, you're not trying to catch up, you're on the front end. Awesome. I'll see you soon.